In this recitation video, we are going to see what is surface integrals and some examples on that. Before we proceed to surface integrals, let us know a little bit about parametric surfaces. When we have a curve and when we parameterize it, we take values of t belonging to some interval a to b and plug them into this curve, which is our t of xti, ytj, and ztk. And the resulting set of vectors will be the position vector for the points on the curve. So for a two-dimensional space D with u and v, we get the resulting set of vectors as r uv, x uvi, y uvj, and j uvk. And the resulting vector will be a position vector on the points of the surface S, which we are trying to parameterize. This equation is generally called as the parametric representation of the parametric surface S. So what we usually need to do is we need to write down the parametric equations for any surface equation provided to us. So basically we are trying to substitute the values of x as x uv, y with y uv, and z as z uv. And these are some commonly used parametric forms of sphere and circle, where x square, y square, z square is equal to r square, where r is the radius. So when we represent it and then convert it to parametric form, we get a is a cos theta sine phi, y is a sine theta sine phi, and z is r cos phi. Similarly, for a two-dimensional space, that is a circle, x square, y square is equal to r square, where r is the radius, then x is r cos theta and y is r sine theta. And usually when we would be given a function or a surface, usually in a plane between like xy or yz or xz. So whenever we are given a plane equation and when we need to convert it into a parametric form, we can use one of these representations provided in terms of x, y, or z. So, and the parametric surface, like once we have this equation and once we plug it in, we have the values of ruv, where it's given from the above equation r x ru, the vector equation position vector x ruv, x uv, y, and then to get the individual forms with respect to u and v, we partially derivate, we get the partial derivatives of the entire equation with respect to a u for each term x, y, and z. And similarly for v, we get as v dx dou x by dou v, dou y by dou v, dou z by dou v. Sometimes you might see theta and phi as well, so we have to get those individual values, whatever we are using, we have to partially derive it with respect to that. So let us take an example. So we have surface integrals. Let us approach with a simple method one, where the limits are known. So in that case, we need to find the surface integral, which is given by the double integral of the function xy. If it z is given, then we can write it in this format xy, because we already have the function in the plane, it's in the xy plane, so z can be represented with g of xy, and under root of dou the given equation g here, this one, with respect to x and with respect to y, take out the partial derivatives and take the coefficient, square it, and then use the formula. So let us see with an example. We need to evaluate the surface integral of xyz ds, which is a part of a plane. Z is 1 plus 2x plus 3y and lies in a rectangle with limits So here we are given the plane equation and the limits. We need to find the surface integral. So we can directly proceed. We have the RHS format. We can use it, the two intervals 0 to 3 and 0 to 2. We have f of x, y and z. So we have x, y, and for z we can substitute 1 plus 2x plus 3y, and when we take dg by dou x, that is, we have the function expected is 2, and dou g by dou y is 3. So using it above, so we have 0, 3, 0 to 2 plus 2x plus 3y and root 2 square plus 3 square plus 1 times. Now for the inner limit dy and the outer limit dx, you can actually use it from here itself. So this comes down to root 14. Now, as from the previous video how we have performed the double integral, we can use the same. Take the inner interval with respect to y. Dx root 14 3. This becomes substituting the limits, 2x plus 4x squared plus 8x times dx, and now taking the integral with respect to x, this gives us This gives us (81 times 14). Therefore, our surface integral of xyz ds is 81 times root 14. Let us see another example of method 1. We need to evaluate the surface integral for a function given by x, and the plane given to us is x plus y 2z equal to 4 between the limits y belonging to 0 and 1. So based on the limits, we can see that it's a unit square. So if we look into the picture, from the equation we have, if this is x, this is y, and this is z, I have 1 unit on x, 1 unit on y, 2 units on z. And the plane would be given by this is of a plane, and this would be our projection. This is the plane J, this is our projection. So we need to find the surface area, surface integral of this. So before we proceed, our equation, so from the surface equation, let's try to calculate the value of x. That is, we have x plus y plus 2z is equal to 4. From this we can take the value of x as 4 minus 2z since the plane is opposite to x and y, we need to consider the value of z from this equation, not x. So we get z has 4 minus x minus y by 2 minus 1 by 2x minus 1 by 2y. That is, z is equal to f of xy. So when we 2 1 by 2 is also 1 by 2. So from the equation we have convert it into this form. Substitute the limits and values. We have 0 to 1, 0 to 1. We have x. The main function is given by x. G is x, y, z is x. And for by 2 whole square plus 1 times dy and dx. So this is given by this becomes root 3 by 2. Since we have x and this, let's try to solve this and see what do we get. With respect to y, this will become y. Therefore, root 3 by 4. That's our the surface integral of g of x, y, z ds. Now let's check out the second type, the parametric form. Using of parametric. So let's evaluate the surface integral of c ds, where s is the upper half of a sphere of radius r is 2. So when we are converting in the method to when we are using the parametric form, the above method one, we can solve the surface integral and by using the formula. So convert the given curve equation of x, y, z into the parametric form with respect to r in this position vector, and then try to the given equation try to find the derivatives, partial derivatives with respect to u and v, that can be theta or phi, and then find the cross product and find the magnitude of the cross product, and then using that we would be able to find the limits as well as the surface integral of it. So here we have this example. We need to find the surface integral of z dot s, where s is the upper half of a sphere with a radius of r. From the above we were able to see the parametric form of the sphere can be is denoted by x is equal to radius r cos theta and sin phi. Phi is equal to r. Z is equal to r cos phi. That is, let us check here. A cos theta sin phi, a sin theta sin phi, and z is equal to r cos phi. So we have the value of r is 2. So when we convert in the parametric form, I have the equation as x2 phi I 2 sine j and phi. And now since we are working with the upper half of the sphere, here the limits for the parameters can be phi, and for phi it would be, because the three-dimensional sphere there is, so in the bottom it would be a circle, so that's why we are considering a value of between, for the value of theta it should be between 0 to 2 pi, and for phi, because of the half, it should be 90. So now we need to determine our theta, which is given by 3 by tau theta. Then we have 2 sine and sin phi I plus sine is cos j, the z term becomes 0, and r with respect to phi is given by sine is cos 2 phi plus sine is cos plus 2, cos is sine, negative sine phi k. Find the cross product of the parameters. Find phi k is 0 and minus 2 sine phi. Let's expand. times 0, so 1 for k. Phi this is minus 4 sine square solving and reducing this is what we get. The cross product minus 4 sine square phi sine theta j minus 4 sine square theta plus cos square theta is 1. Using the identity, we have the cross product, and now the magnitude of our cross product by taking the coefficients of I, j and k square, applying the square and then expanding it from here. If we take 16 sine power 4 phi has common, we get cos square theta plus sine square theta, which is 1, and then which reduces to 16 sine power 4 phi plus 16 sine square phi cos square phi. If we take 16 sine square phi as common, then we can reduce this equation further down to 16 sine square phi, so the entire magnitude is 4 times sine phi. So now coming to the main surface integral, we need to find ds. It's given by d, our main equation, where z is 2 cos phi and the cross product magnitude and cross of cross product is 4 sine phi. And we have obtained our limits from the above as 0 to 2 pi and 0 to pi by 2 for theta and phi. So let's use them. Four times 8 cos phi and sine phi and dt. Using another trigonometric identity or property, we can write this as this is 4 cos to phi. No, wait, sorry, this is sine to phi. And the data. So now using the inner, get sine to phi is minus cos to phi into 2 between 0 to pi by 2 times d theta. Phi by 2. This becomes 4d theta. Respect to theta would be 8 pi. Therefore, our surface integral of z ds is 8 pi. Let us consider another example in type 2 in the parametric form. We need to evaluate the surface integral of y ds, where S is the portion of a cylinder given by square is 3 that lies between so let us begin. Let us write the parametric form of our equation. Since we have the value in z and the angle circle, so we can take z and theta as our parameter coordinates, then this becomes x is radius is 3, therefore 3 cos, okay, here r square is 3, then r is root 3, and root 3 r cos theta plus I root 3. So is 1, and we have limits for z is between 0 to 6, and since it's a cylinder, the base is a circle, so it always lies between 0 to 2 pi. So we have the limits, the parametric form. Now let's find the vector for Rz, that is dou r by dou z, which gives with respect to z, the entire equation doesn't hold any value because theta, and z, this becomes 1, therefore k, and with respect to theta by dou theta, this becomes root 3 cos is sine, sine is cos, and 0. Let's find the cross product. Zero. So we have our cross product, and our magnitude of our cross product can be determined by 0 square root 3 sine theta. Wait. Apologies. This is root 3 cos theta. Square theta plus 3 sine square theta. Root 3. Now let's calculate our surface integral. Between the value of y is root 3 sine theta, and cross product magnitude is root dA. So 3 sine theta. Let's take 3 outside. So with respect to dz, let's see. This becomes 3 times 6 sine theta. Integral of sine is negative cos. Cos 360 is 1 minus 1, 0, 18 into 0. Therefore the surface integral is 0. I hope this helps, and thank you.